Okay, so let me say a few words about the next homework. By the way, how many of you have ever heard of a von Neumann regular ring? Well, it might puzzle you a little bit that you're sitting in a community of algebra class and I define it this way. We say that R is von Neumann regular if for every X in R, you can find some other Y in R, since an X is X, Y, X. Now, the reason I write it this way is because von Neumann regular is also kind of something that people that do non-commutative algebra study as well, right? Of course, it's simplified from the commutative case to X equal X squared Y, right? And so here's something that's, so you might think very fast and loose that Y is almost an inverse for X, not quite, but almost, right? Because X, Y sort of functions like an identity, right? But only on that element X, right? So the first step, whenever you make a definition in math, if you think it's really sexy, is find an example, right? I mean, this is, it's kind of embarrassing when there's this apocryphal story actually that I don't know if any of you have ever heard of this, but I was warned by this by a number theory teacher when I was an undergraduate. So there was this apocryphal story about this graduate student who was studying geometry, topology type things. And the student had come up with a generalization of Euclidean space, right? So it was something slightly more general. And the student wrote the PhD dissertation on this generalization of Euclidean space and proved that this nice generalization satisfied most of the stuff that you would expect to happen in Euclidean space, but there was some stuff that didn't prove. And during his defense, one of the people in the back of the room showed that his notion of generalized Euclidean spaces was equivalent to Euclidean space, right? So that's of course, I think college crucified anyway, so I don't know if that's sort of true, but it does make a good point. Always have an example, right? So here you go. Are there any interesting rings, non-trivial, that are von Neumann regular? How about this? Any direct product or direct sum of fields, an arbitrary direct product or direct sum of fields is von Neumann regular. And notice if you have an infinite direct sum of fields as a ring, that's a ring without identity, right? So these things, the first problem shows that these things actually exist in abundance. Suppose that R has an identity. Show that if R is von Neumann regular, then R is zero dimensional. Let me remind you what it means to be zero dimensional. It means that every prime ideal is maximal. So for example, a field is zero dimensional because the only prime ideal is zero, right? And this is one of my favorite ones, right? And let me contrast here. By the way, Z is not von Neumann regular. Let P equal 2Z, right? Z mod 2Z is very different from Z localized here. Z is odd. In fact, Z mod this prime is a characteristic 2. Z localized to that prime is a characteristic 0. But if you have a von Neumann regular ring, localizing of the prime is essentially the same thing as modding out, which is too weird for color TV, right? But show this is true. This is an interesting little result. That if it's von Neumann regular, modding out by a prime is essentially the same thing as localizing at that prime. Here's a couple of promised problems. Number 4, let R be commutative with identity. Show that if you have a polynomial that's a zero divisor in Rx, that is to say there's a non-zero polynomial G such that f of G is 0, then you can choose G to be of degree 0. Right, that is, it may be chosen to be a constant. So if you have a polynomial that's a zero divisor, you can kill that polynomial with a non-zero constant. Number 5, let R be commutative with identity. Tell me what the units of Rx look like. We know what they look like in the case where R is an integral domain. It's the same as the units of R. What happens if you've got 0 thousands? And finally, number 6, show that V is a valuation domain if and only if V is quasi-local and Bayesian. What direction? So you need to show that if V is a valuation domain, then it's quasi-local, so it's only got one maximal ideal. And it's also Bayesian, which means that every finitely generated ideal is principal. And in fact, that's an equivalence. So if you have any quasi-local Bayesian domain, it has to be a valuation domain. I think I proved this in the notes. You all are graduate students, so don't think if you want to have some excitement over this problem. So. Okay, any questions?
Oh, excuse me.
Yes.
So is there an example like a quotient ring of a polynomial ring, which is from Newman ring?
Okay, I can answer that in a silly way. You can take the entire quotient, right? And so then it's a field, right?
Yeah.
But so what are you looking for? So you're looking at something that's when you say quotient, do you mean like an overring, like a
polynomial ring, like quotients of ideals?
Oh, mod out by.
Oh yeah.
Well, okay, so if you have a polynomial ring, you mod out by a maximal ideal, then it will be a field, which would be von Neumann regular. And I think more generally than that, what you can do, I know how you can do it. What you can do is you can take, so if you just take a polynomial ring in one variable, Qx, right? Now that's a principal ideal domain, so all the primes are maximal. So just pick a list of distinct prime ideals, of the distinct maximal prime ideals, non-zero, and look at the product of that ideal, and then mod out. And by the Chinese remainder theorem, that'll be a product of fields, and that'll give you a von Neumann regular.
Yeah.
Okay. Other questions? All right. So the last time, whoops, let me try this on here. Let me screen back. So last time we had this business that we proved if R inside T, we have U. So this is just some ring extension. U is a unit in a bigger ring. So in particular, you know, if these are domains, you can always do this. If I and R is an ideal proper, then I survives. That is, it remains proper. Right? Or maybe both, you get superluxury. So I'm going to use this for the following theorem, which is going to be very useful. So let's suppose that K is a field and R is inside K. Right. So you just have some field. I mean, the case that I'm going to be mostly focused on is where K is the quotient field R, but it doesn't have to be. Then there exists a valuation domain. There exists a valuation domain. D such that K is the quotient field of V. And I survives in V. Okay, so this is kind of a cool result. So let me think of. So if you start with R and you've got some proper ideal I, and it sits in some field K, which may or may not be a function field in this, then there is a valuation domain. V contains R. I wonder if I said that in there. Yeah. So actually, V is between R and K, such that I survives. And so in particular, this result will hold for K as the quotient field of V. So what that means is, so as a corollary to this, if you have any domain and a proper ideal in it, there's a valuation overring of that domain where that ideal survives. Right. So, by the way, any guesses how we might do this? Quick, read your tattoo.
Doors level.
Right. So let's prove this. So what we want to do here is consider all pairs. RJ, IJ. Right, so consider all pairs RJ, IJ, where RJ is just a ring between R and K, and a proper ideal RJ. And this needs to be a proper ideal of RJ. It contains that. So what we have all, this is a lot of pairs perhaps, right? RJ is just an intermediate ring between R and wherever this field K is. And IJ is sort of an analog of I. It's a proper ideal of RJ that just contains the ideal I. Right? The first thing I claim is, we'll call this set gamma, the collection of all such pairs. Gamma is not empty as the pair R I is in gamma. Right. Because we've got that at the outset. Now, here's the thing. I'm dealing with pairs now, right? So this is just a slightly different twist on the kind of forms one that we've done before. So my set now consists not just of collections of single things, but it's collections of pairs. And so I need to remember this gamma here, if you read those pairs, I want this to be a part of the order set. So well, I've got to define how I order that. We say, let's say there are I sub I is less than or equal to RJ IJ. Anybody want to guess how we get that? Yeah.
Could we just do like containment for both of them? So if RJ contains RI and IJ contains II?
Yeah, that seems like the easiest thing, right? Which is, as we've discussed, almost always a smart way to go in math, at least something to try. And I think that's what we want to do. If and only if RI is contained in RJ and the ideal I sub I contains the ideal I sub j. Right? So even if the ideals are the same, if the rings aren't comparable, then they don't compare. And even if the rings are the same, if the eyes are different, they don't compare. And of course, let me point out that R comma I is contained in every possible pair, right? Because R is contained in every RI and I is contained in every I sub I. Okay, so I claim the coset gamma has a maximal element. And this looks like a job for Captain Zorn, right? So, what do we got to do to be able to apply Zorn's law? Is we have to show that every chain has an upper bound. All right, so let's let we will let T J be T equal to union in I didn't change first. Let's see. Be a change. And what C is equal to these pairs, RI, let's call it J, I, where J is in some index. Now, what I'm going to do is I'm going to let T and J be now I claim T J is an upper bound. Change. That is in gamma. Okay, so what do we need to check? Well, notice that number one, every one of those R J's squeeze between R and K, and so the union of all of ours is still squeezed between K and K. Right, so between R and K. Two, let me go to this bigger one. T is a domain. Is that okay with everyone? I mean, if it's a ring, it has to be a domain, because it's we know it's a subring of a field, right? So it would have to be a domain. Why is it a ring? Right? The important thing here is it's a union of a chain of rings, right? Everybody okay? Everybody comfortable with them? If you have A and B in there, then A and B are at some point in the chain, so just take the maximum of those two, and A plus B is in there. So T is a ring, so it's a domain because it's a subring of a field. We got that. Three. We need this to be a proper ideal. That makes this. Certainly I is contained in J, because I is contained in every one of these. And the union of all these is J, so there's something contained there. J is an ideal. We've done this in source limit all the time, right? Because really what happens is, it's clear also that it's closed under addition, right? Everybody okay with that? And so maybe the one detail I should show is let alpha be J and T, and say T being T. The fact that it's additively closed is the same as the same being a domain. That's not too, and we've done this before. Let me be a little bit careful with this. Suppose alpha is in J and T is in T, then what this means is alpha is in Ri, for some I, and T is in, oh, I'm sorry, I meant to say I sub I, and T is in R sub J, some, then, the index cell. Right? So, notice that if well, notice that if R sub I is contained in R sub J, then this means that I sub I, well, this means that right, so this means that I sub I is contained in I sub J. So alpha is in I sub J. Therefore, T alpha is in I sub J, which is in. So we've got that much, right? What happens if it's reversed? Well, again, T is in R sub J, which is in R sub I. Therefore, T alpha is in I sub J, which is in J. Okay, so it does work as an ideal. So that's good. So where are we now? What do we have? This is a domain. This is an ideal. It contains J. Or I'm sorry, it contains I. And J is proper. Somebody tell me quickly how I know that. That is correct. If not, then one is in J. The J is the union of those other ideals, which means the one has to be one of those ideals, and that contradicts that that's proper. So I think we've just about checked all the boxes here, right? So what do we have here? We have T as a domain, J is a proper ideal, T is contained where it's supposed to be. It's between R and K. J is a proper ideal containing I, right? And so, and let me also note that TJ contains every element of the chain. Right, because it's a unit, it contains every RJ, and J contains every IJ. So TJ is an upper bound to chain C that's in. Everybody okay so far? Yes.
I have a good question. So, if Ri is in Rj, how do we conclude that I is in Ij? Third line down.
Okay, right here.
Yeah, yeah.
Okay, so in this case, Ri is the little one. And so that means that I is the ideal of the little ring. But by hypothesis in this chain, we have to have, so what this means is Ri, which one's Ri is the little one? It's less than or equals. RJ. This is change, and
That's
that's,
by how we define that.
that's exactly right, so this guy's inside.
Okay, yeah.
Right, okay. Okay, so this is indeed, TJ is an upper bound of the chain in gamma, and so we can apply Zorn. And so my Zorn's lemma. Gamma has a maximum element. Which I will call VA. So remember, V is just, this is just a maximum element here. So that is to say that, right, so V is between R and K, and A is proper ideal of this. Okay, so, note A and V proper, because this is the maximal element that we produce by Zorn's lemma, so A has to be a proper ideal. And I is contained in A, again by construction, so I survives in B. Right? So, and I held on to that so long. So we now just wish to show that B is a valuation domain. So we're going to show this evaluation domain. So so suppose U is in K. To show U or U inverse is in K. Correct. That's really it. And so, right. Note the ideal J or not J, A survive in even remember that's what our result was, right? That if you have, notice that VU and VU inverse are both ring extensions of V, right? And so in particular, U is an element of some larger ring, it's a unit in this, so, in one of these two domains, the ideal A must survive by the previous theorem, right? And how does that help us? Since A survives in VU or VU inverse, and the pair VA is maximal, then either VU or VU inverse must be V. Correct? Because there's a maximal element where that I survives. Anything bigger than that, that I in A is gonna blow up. That means that, either VU or VU inverse has to go nowhere, right? And what does this mean? Well, and parenthetically, but this, if VU equals V, then U is in V, and if VU inverse equals V, then U inverse is in V. So V is evaluated. Anybody okay with that? And notice, by the way, that this shows as a side result, and in fact, K is quotient field would be, as a matter of fact. Okay, any questions on that? This is a wonderful result. Because what it says is, let me restrict down to the simpler case where K is a quotient field bar in the first place. If you have any ideal in your ring, that ideal can be stuck inside some valuation. It survives inside some valuation over, right? And that's a powerful thing, because that means that every ideal is strong in a certain sense, and then it continues to live in a valuation domain. And actually, that's getting really close to the quotient field, because if you look at the valuation overrings of the integers, they are zero. Well, there's the silly valuation overring of the integers, all of the rational numbers, right? Just the quotient field. And then you have Z localized at P for all non-zero times P. Notice that those rings are adjacent to the quotient field. There is no ring between Z localized at P and the quotient field, no proper intermediate ring. And so that means that ideals can tend to survive sort of for a long time in this circumstance. But this also gives us something else very important, surprising perhaps even. Theorem. This is one of my very favorite theorems. Let R be an integral domain with quotient field K. And just to remind you the notation, integral closure R bar. Then R bar is the intersection of B intersection taken over all valuation overrows R. This is a big one, right? So if you want to know, by the way, as a corollary to this, integral elements form a ring, because if you believe this theorem, the integral elements are intersections of valuation domains, and intersections of rings are rings, right? So that's kind of a neat little sort of coming full circle observation that I can make. But so if you want to know the integral closure, one thing that you can do is just intersect all valuation. This is right. I mean, the integral closure is just a bunch of roots of mnemonic polynomials until we get this, right? Fascinating. So, before we dive into this proof, you know. Evaluation. How would we prove that? I think we should probably, it would be helpful for us to prove this before we go on to proving this. Thing. I think I actually made the claim earlier, right? It just didn't say much about it, but why is valuation domain interval closed? Yeah, I guess you could do that, but let's do something beforehand. Well, yeah, you guys remember this theorem here? You might remember what the conclusion is. Y'all remember that? And I remember, I remember, I totally dissed on the proof of this, right? I was making fun of it as I go, because it really is just kind of, just pushing around some symbols. How do you suppose this helps us here? Okay, so let's suppose you and K, quote, okay. And suppose U is integral over B. Okay, so let me kind of recouch this. Note that U is integral over B if and only if U is in U inverse. Everybody agree with me? Okay, so let me put this in this is my weapon that I'm going to use later on this. So U is integral over B. If U is in B, then none. Right? Because I'm hoping that all integral elements are in there. If U's in B, none. If not, then what can we say? Well, because the fact is valuation domain, if U is not in B, then U inverse must be, right? But now, therefore, B of U inverse is equal to B, right? And this statement above So starting is that since U is integral, U is in V, U inverse, which is the V. So there it is. So in either case, U is either in V or it's in V, right? Hence, V is integral closed. How many of you know what it means to be completely integral closed? Ever heard of that? I will educate you on that later, I guess. But valuation domains are always integrally closed, and they're almost never completely integrally closed, as a matter of fact. But we'll talk about that later. Okay, so now we know that every valuation domain is integrally closed, so I feel pretty good about that. And this is going to help me here. Notice that. So let's do the pre 416. Notice that each V is integrally closed. Right. And so notice that also I'll leave that as an exercise, but it turns out that if you take a ring, you take its integral closure, the integral closure is integrally closed. Otherwise, it's a bad definition. Completely integrally closed is a bad definition because actually the complete integral closure is not necessarily completely integrally closed. Yeah. Well, see, that's when somebody defines something before the truth is. Right. That's what happened. So what does this give us? So R is contained in V, right? Because by definition, each R is in this intermediate valuation. Right? The V's are defined to be the valuation overrings, right? Therefore, the integral closure of R is contained in the integral closure of V, which is V, right? By that last statement here, right? So R is contained in the intersection. Right? Because each R bar is contained in V, so R bar is contained in the intersection. So hunky dory so far. That's not the interesting part. The interesting part is the fact that the intersection is actually contained in everything that's in the intersection is in fact integral. So for the other containment, suppose X is an element of every valuation over R. Suppose X is in V for all valuation domains V and R. So X is an element of every valuation over N. You need to show X is integral over R. Everybody agree with me? So to this end, I'm gonna pull this tool out again that I did before. Recall that X is integral over R. If and only if X is in R, X inverse. Now, of course, our goal is to show that X is integral. So it suffices to show that X is in R is joined with X inverse, right? So let's suppose not. If X is not in RX inverse, this means that the ideal generated by X inverse is a proper ideal. Right? Because this is generated by the single element X inverse, and when X is not in there, that means that this X inverse is a non-unit, right? So it generates some maximal ideal. Or not maximal ideal, it generates a proper ideal. Everybody okay with that? And so what can we get out of that? Well, since this is a proper ideal, since X inverse in RX inverse is proper, there exists a valuation overring of RX inverse notice that RX inverse and R have the same quotient field because X is an element of the quotient field. So there's a valuation overring of this in which X inverse survives. Everybody agree with that? That was our big thing, right? And now we've totally got this thing beat down because there's a valuation overring of this, hence a valuation overring of R where X inverse survives. So in this valuation ring V, X inverse is a proper ideal. So X is not in V, and there's a contradiction. Because X was supposed to be in every valuation. This is a really super groovy cool theorem, I think. It's very, very powerful. That the integral closure would actually exist as an intersection of such things. Okay, any questions on that? I think this is probably a good place to wrap for today. Any questions out there? Okay, all right. Well, y'all have a good one, and we will see you on Friday.